Dear students, in the previous class, I have explained you the working of an electrochemical cell. I hope you must remember that there were two half cells which were externally connected by an insulated wire and internally they were connected through a salt bridge. I also explained the working of the salt bridge. Now today I am telling you how to represent a cell, that without seeing the beakers, without seeing the two half cells, how you will know that which half cell will undergo oxidation and which half cell will undergo reduction, which is anode and which is cathode. Let me tell you the representation of an electrochemical cell. Anode is on the left hand side and cathode is on the right hand side. The salt bridge is represented or indicated by a parallel line in between the anode and the cathode. Anode we will write on the left hand side and cathode on the right hand side. You can see and you must be remembering that in the previous class the zinc electrode was acting as anode and the copper electrode was acting as cathode. Zinc was losing electron and the copper ions were accepting or gaining those two electrons. Now just see how to represent the zinc half cell or the oxidation half cell and the reduction half cell. Zinc semicolon zinc ions or zinc a vertical line and the zinc ions. For more specification you can put concentration also with the zinc ions. 1 molar is representing the concentration. This is the anode side. So you can see that the anode side is written first the metal and then its ionic state. While writing the cathode side, first we will write the ionic state, the copper ion, then the semicolon or a vertical line, its concentration, and then the copper atom in the solid state. And in between the two half cells, you can see the parallel lines. These parallel lines are representing a salt bridge. I hope this is very much clear to you that how we can represent an electrochemical cell. And you must understand this to solve the numericals. Let me give you a memory aid, that how to remember that which side is anode, which side is the negative terminal or which is cathode or a positive terminal. Dear students, just remember one word, lone, L-O-A-N. L means the left and the loss of electrons. O means oxidation. A means anode and N means negative terminal. Now it is very much clear that on the left hand side the loss of electrons takes place. The loss of electrons is known as oxidation. Oxidation takes place at anode and anode is the negative terminal. Just reverse everything and you will get the other side, that is the reduction side. If the left hand side the loss of electron, then on the right hand side it is the gain of electron. And if on the left hand side the loss of electron is oxidation, then on the right hand side it is reduction and it takes place on cathode and cathode is the positive terminal. Let me give you another memory aid. You can use any of either. That is the alphabetical order. Both the sides are written on the screen and you can see L is left, then its counterpart is right, and we know that R always comes after L when we write the alphabets in sequence. O oxidation, R is reduction, A is anode, C is cathode, N is negative, P is positive. We know that R, C or P always comes after A O, A and N. The electrode potential of the galvanic or the Daniell cell is 1.1 volts. The concentration of the zinc ions and the copper ions are taken as unity. Now let me explain few terms which you must know as a definition or for the further concepts of solving the numericals. Electrode potential. Electrode potential is defined as the potential difference between the electrode and the electrolytic solution, or you can simply say as electrolyte. If there is no electrode potential, there will be no transfer of electrons. As we know that the heat only transfers when there is a temperature difference. Always heat transfers from hot body to cold body. In the same way, whenever there is an electrode potential, there will the movement of electrons. When the concentrations of all the species involved in the half cell is unity, then the electrode potential is known as standard electrode potential. And earlier I have told you that the direction of the flow of the current is opposite to the electron flow. Cell potential. Cell potential is the potential difference between the two half cells of the galvanic cell. The unit of the cell potential is volts and the apparatus which we use to measure the cell potential is voltmeter. Now how to measure this electrode potential? What formula we will use to calculate the electrode potential? Let's see that. EMF, electromotive force or cell potential. The formula is E cell is equals to E right minus E left. And I hope now you know that on the right hand side we have cathode and on the left hand side there was anode. So we can also write this formula as E cell equals to E cathode minus E anode. And very important point to note is, for calculation of EMF of the cell, the electrode potentials are always taken as reduction potentials. EMF is slightly different from the cell potential. EMF we say when the cell is not sending any current or a negligible current, that is just in the beginning when the cell just starts working, at that time the potential difference is known as electromotive force. In short we say as EMF. Dear children, the cell potential which we measure by using the formula E cathode minus E anode is the relative value of the cell potential. It is not the absolute value. To measure the absolute value of the electrode potential, we need a reference electrode. Standard hydrogen electrode is universally accepted as a reference electrode. Let me explain you this SHE or NHE. The full form of SHE is standard hydrogen electrode, and SHE, which is also known as NHE, is normal hydrogen electrode, commonly known as reference electrode. Let's see its working. Standard hydrogen electrode is a reference electrode to measure potential of individual half cell. It has been assigned a zero potential at all temperature. Its construction. Standard hydrogen electrode is made up of a platinum wire coated with platinum black and is enclosed in a glass tube. We use platinum here because it is an inert element. It does not react with any other electrolyte or any other metal. And the SHE is a reversible hydrogen electrode because it can undergo the oxidation as well as reduction. This platinum wire enclosed in the glass tube is known as the platinum electrode. It is dipped in the hydrogen ions, which the concentration is 1 molar. The hydrogen gas is constantly bubbled through this solution at 1 atmospheric pressure. This is the standard hydrogen electrode, which can act as anode as well as cathode depending upon the other half cell. Earlier I have told you, arbitrarily its potential has been fixed as 0 volts. Now let me explain you both the reactions, how it can undergo oxidation, that is the loss of electron, and how it can undergo the reduction, that means the gain of electrons. Just see that. As anode, you can see hydrogen gas loses 2 electron and is oxidized to hydrogen ions. And when it has to act as cathode, that means the gain of electron, then hydrogen ions in the electrolyte, they accept or gain the 2 electrons and is reduced to hydrogen gas. So I think it's very much clear that it can act as anode and cathode. So we say it as reversible hydrogen electrode. Just see the reaction, the conversion of the elemental state into the ionic state and the reverse reaction. In the figure, now you can see that the standard hydrogen electrode is connected to another half cell. It is a nickel half cell. SHE acts as the other half cell, and you can see that the two cells are internally connected through a salt bridge, the function of which has been clear to you in the previous class. The cell potential which we measure is the cell potential of the other half cell which is connected to the standard hydrogen electrode just by simply using the formula E cathode minus E anode or E right minus E left. We can find out the cell potentials of the various cells. In the given example, you can see with the hydrogen electrode, the copper half cell is connected. As you can see from the representation of the half cell, the hydrogen cell or the standard hydrogen electrode is acting as anode because it is written on the left hand side of the parallel lines, and the copper electrode is written on the right hand side of the parallel lines. Now simply using the formula E right minus E left, we can write 0 for the hydrogen electrode. So the ER, that is the potential of the right hand side electrode, which is a copper electrode, comes out to be 0.34 volts. This is the electrode potential of copper half cell. By connecting various half cells with the standard hydrogen electrode, we have calculated the potentials of the various half cells, and they are arranged in a series known as electrochemical series. Just by taking the values from the electrochemical series and putting these values in the formula E cathode minus E anode, we can find out the cell potentials without actually connecting the two half cells. And let me once again tell you the use of the platinum electrode. It is an inert electrode and it just provides the surface for the inflow and the outflow of the electrons. Dear students, just now I have explained you how to represent an electrochemical cell and the need and use of standard hydrogen electrode, a reference electrode whose potential has been fixed as 0 volts, and how we can use the electrochemical series to find out the cell potential of the various combinations. I hope now you can use the formula E cathode minus E anode in your numericals and find out the cell potential.